Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Gauss Divergence Theorem, Part 2. So in the last session, I have introduced the Gauss Divergence Theorem, which transforms a surface integral into a volume integral, and also solved one problem on Gauss Divergence Theorem. So we verified the theorem for the given vector function. In verification, we need to find both LHS and RHS, and finally we have to show that both are equal. And today I am going to solve one more problem on Gauss Divergence Theorem, which is an application of Gauss Divergence Theorem. By transforming into triple integral, evaluate the double integral, where S is the closed surface consisting of cylinder and the circular discs Z equal to 0 and Z equal to B. So here we need to evaluate this surface integral by transforming into triple integral. So that means we use the Gauss Divergence Theorem. By Gauss Divergence Theorem, surface integral f bar dot n bar ds is equal to volume integral div f bar dv. So to transform a surface integral to volume integral, first we need to calculate this div f bar. For that we need f bar. But in the given, the surface integral x cube dy dz plus x square y dz dx plus x square z dx dy. This is the given surface integral over S. So a surface integral can also be represented, surface integral can also be represented as the double integral f1 dy dz plus f2 dx dz plus f3 dx dy. So here this is the first component f1 of the vector f, and this is f2, f3. By comparing these two, it is clear that what is the component f1? Here x cube. X cube is the component. So f1 equal to x cube. Then f2 x square y and f3 x square z. So that implies we can find f bar as f1 I bar, f2 j bar and f3 k bar. If we have the vector f bar, we can find the divergence of f bar also. So coming to that, therefore div f bar is, we know that div f bar is del dot f bar, the dot product between the gradient operator and the vector f bar. So which is the sum of the products of corresponding components. So dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So dou f1 by dou x, we need to calculate those values also. So here we have f1 is x cube. So dou f1 by dou by dou x of x cube plus dou by dou y of second term, second component is x square y plus dou by dou z of f3 x square z. Now differentiating partially with respect to x, here we get 3x square, with respect to y, so x square constant, for y we get 1, plus with respect to z, x square constant, for z we get 1. So total 3x square plus x square plus x square, that is 5x square. So therefore the surface integral f1 dy dz plus f2 dx dz plus f3 dx dy, that is equal to volume integral div f bar dv. That means triple integral 5x square dz dy dx. So if we have the limits, then we can integrate this. Now the limits. To find the limits, use the given data. So S is closed surface consisting of cylinder and the circular discs. So here Z equal to 0, Z equal to B. That denotes Z changes from 0 to B. And also it is given the cylinder x square plus y square is equal to a square. From this we can find the value of y. This is equation 1. Y square is a square minus x square. Y is plus or minus root a square minus x square. And therefore y changes from minus root a square minus x square to plus root a square minus x square. Now to find x limits, put y equal to 0 in 1, which gives x square value as a square. From that we can find the value of x as plus or minus a. Therefore x changes from minus a to plus a. So therefore we have all three roots. Therefore we have all three limits. Hence the given surface integral is equal to, so x from minus a to plus a, and then y from minus root a square minus x square to plus root a square minus x square, then z from 0 to b, 5x square first with respect to z, then y, then x. So 5 constant, x from minus a to plus a, and y from minus root a square minus x square to plus root a square minus x square. Then x square is constant. Integral dz is z from 0 to b. This is b. dy dx. Then 5 into x from minus a to plus a. I can write upper limit, this upper limit is b. So here we get b minus 0, which is b outside. Now x square is there, we need to integrate with respect to y. So x square into integral dy is y, y from minus to, before going to this, here we can do one thing. So let us delete this. Okay, now here, since the integrand is constant, here we have to integrate with respect to x, which is having even power. For y, there is no term, y term, so constant. So since the integrand is constant, we can write this as 5 into 2 into 2, x from 0 to a, y from 0 to root a square minus x square, x square into upper limit is b, lower limit is 0, dy dx. So what is the property? Integral from minus a to plus a, f of x dx is 0 if f is odd, and is equal to 2 times of 0 to a f of x dx if f is an even function. So since the integrand is even, so that implies 20b x from 0 to a, x square into, now integral dy is y, and 0 to root a square minus x square. So 2 times integration is over, and hence that is equal to 20b into integral from 0 to x from 0 to a, x square into, now upper limit is root a square minus x square, lower limit is 0 dx. Now the third time integration is with respect to x. So if it is possible, we can integrate this as it is, or otherwise for our convenience or for simplicity, we can transform x to any other parameter. For example, let us put x equal to a sin theta. Then what happens? Dx is a cos theta d theta, and limits. If x is 0, then sin theta is 0. That implies theta is 0. If x is a, then a sin theta is a. So sin theta is 1. That implies theta is pi by 2. So therefore, this is equal to 20b theta from 0 to pi by 2 x square a square sin square theta under root a square minus x square, again a square sin square theta, dx is a cos theta d theta. So this is 20b theta from 0 to pi by 2 a square sin square theta. Here a square common, so a comes out, and integral root 1 minus sin square theta, and again one more a cos theta d theta. So finally 20b a square a power 4, that comes out theta from 0 to pi by 2 sin square theta into 1 minus sin square theta is cos theta into cos theta, so cos square theta d theta. So which is 10 into b a power 4 theta equal to 0 to pi by 2. Let us write this 20 as 10 into 2. So actually we need 5 into 4 is 20. So I'll write this as 2 square sin square theta cos square theta d theta. So that's equal to 5b a power 4 theta from 0 to pi by 2. I can write this as 2 sin theta cos theta whole square d theta, which is 5b a power 4 theta from 0 to pi by 2 sin 2 theta whole square, so sin square 2 theta. Now to find this integral, again we need to use the formula cos 2 theta equal to 1 minus 2 sin square theta. So from this 2 sin square theta is 1 minus cos 2 theta. So sin square theta is 1 minus cos 2 theta by 2. But here we have the angle 2 theta. So put theta, replace theta by 2 theta. Sin square 2 theta is 1 minus cos 4 theta by 2. So let us use this substitution 5a power 4 into b theta from 0 to pi by 2 1 minus cos 4 theta by 2 d theta. So this is 5 by 2 a power 4 b. Now integral d theta is theta minus integral cos is sin. So sin 4 theta by 4 from 0 to pi by 2. Now applying the limits, we get upper limit is pi by 2 minus sin 4 pi by 2 by 4 minus lower limit is 0, 0. So this is sin 2 pi. We know that sin n pi is always 0. So this also becomes 0. So only pi by 2 remains 5 a power 4 b pi by 4. So hence the given surface integral is equal to 5 a power 4 b pi by 4. Similarly, let us solve one more problem. Evaluate the surface integral ax square plus by square plus cz square ds over the surface of the sphere x square plus y square plus z square equal to 1. So again we can use the Gauss Divergence Theorem. We can take the help of Gauss Divergence Theorem, which converts or which transforms a surface integral to volume integral. So given surface integral f bar dot n bar ds is surface integral ax square plus by square plus cz square ds. So here we can apply the theorem, or we can use the theorem if we have the vector f bar. But in the given problem, f bar is not given. So we need to identify that vector, or we need to find that vector from the given. And what is n bar? N bar is the unit normal vector to the surface S. What is the given surface here? X square plus y square plus z square is equal to 1. So let phi equal to x square plus y square plus z square minus 1. And how we get the normal vector? By finding del phi. Del phi is the normal vector, which is I bar dou phi by dou x plus j bar dou phi by dou y plus k bar dou phi by dou z. So here we have phi. So dou phi by dou x with respect to x, 2x, dou phi by dou y, 2y, and dou phi by dou z is 2z. So therefore, our del phi, the normal vector is 2x I bar plus 2y j bar plus 2z k bar. And now the normal vector, unit normal vector n bar is del phi by mod del phi, which is 2 common xi bar plus yj bar plus zk bar divided by under root 4 x square plus 4y square plus 4z square. So that implies n bar is 2 times xi bar plus yj bar plus zk bar divided by this 4 comes out, under root 4 is 2, and under root x square plus y square plus z square. So these 2 gets cancelled, and what is x square plus y square plus z square? That is 1. That implies our n bar is xi bar yj bar plus zk bar. So we got n bar and we have f bar dot n bar. From these two we need to find out what is f bar. So therefore we have f bar dot n bar is ax square plus by square plus cz square, and n bar is xi bar plus yj bar plus zk bar, which we have obtained just now. Now that implies I can write this f bar dot n bar, this one as ax I bar byj bar czk bar dot xi bar yj bar zk bar. Now by finding the dot product between these two, this is ax square plus by square plus cz square. So this is our n bar. If this is n bar, this should be f bar. Hence f bar is ax I bar byj bar cz k bar, which is in the form f1 I bar f2 j bar plus f3 k bar, component form. So now by Gauss Divergence Theorem, surface integral f bar dot n bar ds can be obtained by transforming into volume integral of div f bar dv. So we need to find div f bar first. Now div f bar is del dot f bar, which is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Now dou f1 by dou x, here we have f1 is ax, so with respect to x we need to differentiate this partially. So then we get a dou by dou x of ax is a plus dou by dou y of by is b, dou by dou z of cz is c. So hence a plus b plus c. Div f bar is a plus b plus c. Now by Gauss Divergence Theorem, surface integral f bar dot n bar ds is volume integral div f bar dv, which is the limits. Now we need to find the limits. But here in this particular problem, since there is the function is a constant function, so here a plus b plus c is a constant value. So I can write this outside integral dv over v. So integration and this differentiation gets cancelled, and hence we get a plus b plus c into v. But what is the surface here? The given region is a cylinder. So hence the surface integral f bar dot n bar ds is equal to 4 pi by 3 into a plus b plus c. Since this 4 pi by 3 is the volume of the cylinder, of unit radius. So here after integrating we got V. That V denotes the volume of the cylinder, and we know that the volume of the cylinder is 4 pi by 3. Hence the surface integral is 4 pi by 3 into a plus b plus c. In today's session we have solved two problems on Gauss Divergence Theorem as applications of Gauss Divergence Theorem. To use the Gauss Divergence Theorem, what is the advantage of Gauss Divergence Theorem? We can transform a surface integral into a volume integral. So, evaluate the surface integral using Gauss Divergence Theorem means we transform it to volume integral, or sometimes evaluate the surface integral. And to evaluate the surface integral, we need to find the integral over each surface of the given region. Instead of finding that, we transform it to volume integral, and if we have the limits of x, y, z, it is very simple and easy to solve or evaluate that volume integral. Hence, we transform the surface integral into volume integral with the help of Gauss Divergence Theorem. This is for today's session, and we will meet in the next session.